In this video, I'm going to work through the 4.1 homework exercises on web work. In Chapter 4, we're studying exponential functions and logarithmic functions. And so the first problem in 4.1 is to look at some graphs of some typical exponential functions. So we have 5 different graphs, and we have to match the colors of the graphs with the corresponding functions. And they give us a hint here to look at f of 0 and f of 1. And so by finding 2 points on each of the graphs, you can actually match up the corresponding graph. If we look at the first function, f of x equals 2 to the x, we see with these exponential functions, the input becomes the exponent on the base 2. Number 2 is called the base, and x is the exponent. So if you plug in 0 for x, you would get 2 to the power 0, and 2 to the power 0 equals 1. So this tells us to look for the point 0, 1 on the graph. And if you look at f of 1, that would be 2 to the power 1, which equals 2. So the point 1, 2 is on the graph of 2 to the x. Now when we look at the graph, we notice that the scale goes up by 2 here, and each one of these little dots is actually 1/5. So the vertical scale is not exactly that helpful. If we look on the red graph, we see that this point right here is at 0, 1. So the red graph right here is 2 to the x. So when I'm entering my answers, I'm going to put an R for red. Now, we've learned about transformations of graphs, and so we can actually use that to figure out the rest of these graphs. 2 to the x plus 1 would be the red graph shifted up 1 unit. And so if we compare, the green graph above here is exactly 1 unit above 2 to the x. So for the second graph, f of x equals 2 to the x plus 1, this would be the green graph, and I'll put a G. If I start with the original red graph and I move it down 1 unit, I would end up with the yellow graph here. And so the yellow graph would be 2 to the x minus 1. The other two transformations, 2 to the x plus 1 and 2 to the x minus 1, are horizontal shifts. If you replace x with x plus 1 in the exponent, the graph would be shifted left 1 unit. So if we start again with the red graph and we shift it left 1 unit, we would end up with this purple graph. It looks kind of like magenta to me, but I call this a purple graph. So 2 to the x plus 1 would be the purple graph, and I'll put a P for purple. And then the last transformation, if I take the red graph and shift to the right 1 unit, I'll end up with this blue graph. And so that would be 2 to the x minus 1. And we got it right. So you can enter lowercase answers or uppercase answers for matching these graphs. Now you could also just graph these functions on a graphing calculator or a graphing utility like Desmos.com and match up the corresponding graphs. Let's move on to problem number 2. All right, so in problem number 2, we're given 6 population functions, and we have to answer certain questions. So these population functions are exponential growth functions. When you're looking at an exponential growth function, the constant term in front of the parentheses would be the initial population. Then we have 1 plus the growth rate, r, raised to the power t. So r is called the growth rate, or if r is negative, we call it the decay rate. So we see that when we answer these questions, like which town is growing, which town is shrinking, if the whole base is a number bigger than 1, then the town is growing. If the whole base 1 plus r is actually less than 1, that means that r was negative, and therefore the town is actually shrinking. For part A, when we're asked to find which towns are growing, we just look to see which functions have a base that's bigger than 1. So in town 1, the base is 1.191, which is bigger than 1, so it's growing. Town 2 is shrinking because the base is smaller than 1, it's 0.8. Town 3 is shrinking. Town 4 is growing because the base is 1.08. And then we see town 6 is also growing because the base is bigger than 1. For part B, we're asked to find which towns are shrinking. So again, we're looking for when is the base of the exponential less than 1. If the base is less than 1, that means that the growth rate, the value r, is negative, and so it's actually a decay rate. So the towns that are shrinking are towns 2, which has a base of 0.8. Town 3 has a base of 0.94, and town 5 has a base of 0.79. Question C asks which town is growing the fastest. So that would be the one that has the largest base. So we're talking about the 1 plus r. That's your base here. So we're trying to see which one has the largest base. It looks like town 1 has a base of 1.191, and then it says what is the annual growth rate of the town as a percent. So 0.191 is as a decimal represents a growth rate percentage of 19.1%. So that is the growth rate of town 1. For part D, we're trying to find which town is shrinking the fastest. So which town has the smallest growth rate? So of all the shrinking towns, 2, 3, and 5, 2 has a base of 0.8, 3 is 0.94, and 5 is 0.79. So the smallest base would be for town 5, 0.79. So if we think about 0.79, that is the base 1 plus r. So we can see the decay rate here. If I subtract 1 from both sides, we get a rate r of negative 0.21. So a negative growth rate of negative 0.21 tells us that the decay rate is 21%. 0.21 is 21%, and since it's negative, it's actually a decay rate. So town 5 is shrinking the fastest at a rate of 21% decay. Now for parts E and F, it says which town had the largest and smallest initial population. So now we're looking at the coefficients in front of the parentheses. So we're looking at now the initial population. So which town had the largest initial population? It's town 2, because 2,700 is the largest. And then which town had the smallest initial population? That'd be town 6. So town 6 would have the smallest initial population, which is 500. So I entered all these answers in WebWork and submit my answers, and we have correct answers. Okay, let's move on to problem number 3. So problem number 3, we have a population of animals in year T given by this formula. P equals 1400 times 0.84 to the 12t. It says find the monthly percent decay rate in P. So we're looking again at this base. We see that the base of 0.84 corresponds to the 1 plus r. That's the base of the exponential. So this is where we need to look to find the decay rate. So if 1 plus r is equal to 0.84, then the decay rate, again, of subtracting 1 from both sides, would equal negative 0.16. So this is a decay rate because it's a negative number. Well, that corresponds to 16% decay rate. So what it is saying is that this population is actually losing 16% every month. So let's enter that in WebWork. Submit. So all we have to do is look at the base 0.84 and determine that the decay rate is 16%. Let's move on to problem number 4. So for problem number 4, we're given that a population of 4.1 million people grows at a constant percentage rate. So this is an exponential growth problem. It says, what is the population 1 century later? And we have two different conditions. In part A, we have an annual growth rate of 2%. So when we set up the expression for this population, we just have this accumulated amount equals the initial population size P times 1 plus R, the growth rate, raised to the power T. So to model this growth, we have the accumulated amount will be, I'm going to use 4.1 to represent 4.1 million. The growth rate, R, is 2%, but we use the decimal form 0.02. So when I plug that in for R, I get 1.02 to the power T. So now this function would represent the size of the population after T years. So if we want to find 1 century later, we would plug in 100 for T. And so we see that in 1 century, this would equal 29.703. And that represents 29.703 million people. Now for part B, we're told that we have a continuous growth rate at 2%. So for continuous growth, we use this formula. A equals P, which is still the initial population, times e to the RT. E is a special exponential constant. It's about 2.718. So now with this formula, we use 4.1 again for the initial population, E, and then we raise that to R times T. So R is still 0.02 and T is 100. So when you enter this expression into a calculator, you will get 30.2951. So when putting in answers in WebWork, it's often appropriate to leave several decimal places. And in the wording of the problem, it actually says leave 3 decimal places. So I'm going to enter 30.2951. Submitting our answers. We'll see if we get the correct answer. Let's move on to problem number 5. All right, problem number 5, we have another population model, and we are asked part A to find f of 0. So finding f of 0, we could plug in 0 for t, but we see that this is going to give us 1.029 to the power 0, so that just equals 1, and we'll just end up with 950. So we recognize f of 0 as our initial population size. For part B, we have to find f of 10. So this would represent the population in year 10. So we just have to put a 10 in for the exponent t, and evaluating this expression, we get 1,264.379. Again, I'm going to use at least 3 decimal places when entering our answer. So now f of 10, that represents the population in year 10. So that's what part C is asking. It says, which of these statements correctly explains the practical meaning of the value you found for f of 10? Well, f of t is the population in year t, so f of 10 would be the population in 10 years, or in year 10. So that would be option B. And in part D, it says, if the percentage growth rate remains constant, approximately when will the population reach 2,200 people? So to solve this exactly, we would have to determine when is f of t equal to 2,200. So to solve this exactly, you would set 950 times 1.029 to the power t equal to 2,200. In order to do this, we would have to use logarithms to solve an exponential equation. But we're going to actually solve this graphically. So I'm going to graph f of t and just look to see on the graph, since we only have to round to the nearest whole number year, the easiest solution would be to graph this function and then just see when it reaches height 2,200. So here's the graph of f of t equals 950 times 1.029 to the t. And we see that the graph is reaching height 2200 about at this point right here. And look, it's 29.3 is 2195.301. So the closest year would be year 29. So it's in between 29 and 30, but it looks like it's a little bit closer to 29 when the function is exactly at height 22. So from looking at that, 2200. So from looking at that, our answer is year 29. So we see that t is approximately 29 when the function is at height 2200. So I enter these answers in WebWork and submit, and we've got correct answers. So moving on to problem number 6, we are looking for answers using compound interest. In problem 6, it says, what is the balance after 1 year of an account that contains $1,500, which earns a yearly nominal interest rate of 8%? And we're going to compound these answers, compound the interest in 4 different ways: annually, weekly, every minute, and continuously. So for this compound interest problem, there's actually a nice formula for calculating compound interest, and I'm going to pull up the class Blackboard page. So when you look at the class Blackboard page on the Chapter 4 tab, I have a link to the formulas that will be needed for Chapter 4, but there's also, on the second link, is a worksheet for compound interest. So if you click on that, you can see the formulas that we're going to use for calculating compound interest. So the accumulated amount in the account is going to be equal to the initial principal, that's the amount that you invest, times 1 plus r, the interest rate, divided by n, the number of compoundings per year, that's the number of times you calculate the interest, raised to the nt. And then on the bottom, we'll see when we use compound interest, we'll use the formula that we used in a previous problem, p times e to the rt. That's only for continuously compounded interest. So back to WebWork. We have to find interest compounded annually. Well, for this problem, our principal is going to be $1,500. The amount of time, it says after 1 year, so we're just going to use 1 for t. And then we have a interest rate r of 8%, so we're going to use 0.08 in our formulas. So for the first 3 problems, we're going to change the number of n. So for part A, when you're compounding interest annually, that's just 1 time per year. So n equals 1. So the accumulated amount will be 1,500 times 1 plus 0.08. I'll write divided by 1 even though I don't need to. And then times 1 to the times 1. So 1 for n and 1 for t. So really we're just adding 8% to 1,500, and this will give us an accumulated amount after 1 year of $1,620. In part B, we're computing the interest weekly, so every week that would be 52 times per year. So our accumulated amount will be 1,500 times 1 plus 0.08 divided by 52 raised to the 52 times 1. So this expression, when evaluated in a calculator, should be close to 1620, but each compounding will add a little bit more interest, so you should get a little answer slightly bigger, and we do. We get $1,624.83. So we're rounding to 2 decimal places because this is dollars and cents. In problem C, we're looking at the fact that when we compute interest, the more compounding adds a little bit more interest, but there's a limiting amount. So when we're computing interest every minute, we're going to use 525,600 for n. Then in our accumulated amount formula, we would have 1,500 times 1 plus 0.08 divided by this number n, 525,600, raised to the 525,600 times 1. And even though we've used 100,000 times more compoundings per year, we're not going to get that much more interest. So when you evaluate this, you end up getting $1,624.93. So even though we had so many more compoundings, they only gained us 10 cents of interest. So this is kind of leading up to part D. When we have continuously compounded interest, this would simulate going to letting n go to infinity. So letting n be extremely large, you would get the same as when we use this formula for continuously compounded interest. P times e to the RT, 1,500 times e to the r, which is 0.08, times t, which is 1. And when we do 1,500 times e to the 0.08, we get 1624.93. So this number rounds to the same answer when you go to 2 decimal places, but it will be slightly larger than the expression we got in part C. And submit our answers. And there we go. So problem number 7 actually has some more complicated algebra involved. It says that a sum of $850 is invested for 10 years, and the interest is compounded quarterly, which would be 4 times per year. It says there's $1,000 in the account after 10 years. What was the interest rate? So again, we're going to be using these compound interest formula, and we're going to plug in all the given information. Well, the accumulated amount would be A, so that would be $1,000 after 10 years. And the initial investment was $850, so that would be P. And we're not given the rate R. That's the answer what we're trying to find. We're told that it's compounded quarterly, so that would be n equals 4. And so we plug in 4 for n here, and then this after 10 years. So this is the expression we need to unravel and solve for the interest rate R. The first thing I'm going to do is divide both sides by 850. So I get 1 plus R over 4, the quantity raised to the 4 times 10, so that's the 40th power. That will equal 1,000 divided by 850. So to unravel the next step, to get rid of this parentheses to the power 40, I would take the 40th root of both sides. Another way of writing that is the 1 over 40th root of both sides. So I have this expression on the left, 1,000 over 850. And taking the 40th root, or the 1 over 40th power, that will equal 1 plus R over 4. So the next step would be to subtract 1 from both sides. That will equal the interest rate divided by 4. And then finally, multiplying both sides by 4, I would get 4 times 1,000 over 850 to the 1/40th power. And when I multiply the minus 1 times 4, I get minus 4. So that would give me my rate R. So when I evaluate this expression, I will get 0.01628. So this is the value of the interest rate. So we have to write this and our answer in a percentage form. So moving the decimal place over to the right 2 places, we get 1.628%. And there we go, we got the correct answer. So moving on to problem number 8, we're told that Gordon has heard that fusion-powered SUVs will be available in 10 years at a price of $150,000. How much should he invest now at 8.7% to have the amount required to purchase the SUV in 10 years? So this is an annual growth rate problem, so we're just going to use this simple exponential growth formula. And he wants the accumulated amount to be $150,000 in 10 years. But the question is, what is the initial investment, P? So we have a rate R of 8.7%. So in the formula, we're going to use 0.087. So 1.087 will be our base. And then we want this to be invested for 10 years. So we need to solve for P. This might look like a complicated problem, but it's actually just one step. We just need to divide both sides by the expression 1.807 to the power of T. So this is just a multiplication factor times P. So we're just going to divide both sides by this constant. So we'll get 150,000 divided by 1.087 to the power 10, and that will give us our initial principal P. So when we evaluate this value of P in our calculator, we get 65,132.21. So if you have $65,000 sitting around and you want to invest it for 10 years at 8.7%, then you'll have about $150,000. So I'm going to enter this expression in WebWork and submit. And there we go. So we want to round to 2 decimal places because this is in dollars and cents. And that finishes the 4.1 homework.